Welcome back again. We were discussing yesterday that how the prime numbers are distributed, and specifically we have seen that there are infinite number of primes, and also we saw that there are infinitely many primes of the form 4n plus 3. 4n plus 3, where n is integer. I mean natural number. Okay. To prove this, we used a method where we have used the concept that the product of two numbers of the form 4n plus 1 or two or more numbers of this form is again a number of this form. Okay. So what we have used that 4n plus 1 4m plus 1. And we have seen that this can be written as 4 times of mn plus m plus n, I guess. And then what is there? Just a minute. Let me multiply it. 16 mn and 4n plus 4m. Anything remaining? 1 is remaining. Okay. So what we can write? We can write like this. 4 we can take common, and then 4mn, then m plus n, and 1. So because m and n are integers, so we can write this is 4 mn. Suppose we are writing it for s and then 1. So any numbers, if we are taking some numbers or finite numbers of terms like this, and we are finding out product of them, then we are getting another number of this form. Okay. So we use the same technique that when we wrote that n in the form 4q plus 1, 4q, 4q plus 3, we have written this number. And then we claimed that the divisor of this are going to be the divisor of this are going to be numbers, some numbers of the form 4n plus 1, and some of the divisors are of the form 4m plus 3, and at least one divisor should be there of this form. Okay, so this was the technique we used to prove that there are infinitely many numbers of primes of this this form. Similarly, there is another result. Uh, there is another result that there are infinitely many primes of the form. The next result is there are infinitely many primes of the form 4m plus 1, like this. Okay, so you can prove in a similar fashion, or there are some different proof also. You can try it out. Next, let us see a conjecture. This is called Goldbach conjecture. Goldbach conjecture. Before that, what is conjecture? Do you know? What is a conjecture? Just like we say that what is a proposition, what is a lemma, what is a theorem. Okay, theorems are proved, or state theorems are proved using the help of lemmas. And in fact, lemmas are tools which are used to prove a theorem. In other words, we can say. And lemmas are nothing but some statement and implications. Okay, and a similar thing is with also there with the theorem. Okay, Proposition is a statement which is either true or false. Okay. Proposition is a statement which is either true or false. You cannot say that it is sometimes true or sometimes false. There should be a clarity. Okay. So these are the things. Anyway, so what is a conjecture? Conjecture is a statement which seems to be true, but which has not been proved yet. All right, which seems to be true, but not proved yet. Okay, but there are sufficient number of evidence which are supporting that the given statement is true. Okay, so the conjecture is that Goldbach conjectured that he predicted based on certain examples that every even integer greater than 4 is the sum of two primes. Okay, for example, uh, Goldbach is talking about any integer greater than 4. So for example, greater than or equals to 4. So let us take 4. So we can write 2 plus 2. And let us take 6, another even integer. So this can be written as 3 plus 2, 3 plus 3. And 8, another even integer. This can be written as 3 plus 5 or 5 plus 3. And 10, this is 7 plus 3. Or you can write it another way also, 5 plus 5. This, you can write it like this also. Okay. Or 16, we can write 11 plus 5. What about 12? Can you write this? How we can write 12 as sum of two primes? 7 plus 5?
Plus 5.
Yeah. What about 14? 7 plus
7 plus
7.
7.
So like this, based on this pattern, Goldbach conjectured that if you are taking any even integer of this like this, then it can be written as the sum of two primes. So two primes P and Q may be same. Also, there is no harm in assuming that. So let us see the statement of this conjecture. This it states that every even integer greater than 4, greater than or equals to 4, is the sum of two primes. Okay, so this conjecture is not proved yet, in fact, but in 1973, Chen Jing Run, 1973. Chen Jing Run, R-U-N, Run. He proved that every sufficiently large even number, every sufficiently large even number, even number or integer, we can say integer has the form n equals to p plus q, where p is a prime, and q is the product of at most two primes. At most two primes. So he's telling about sufficiently large even number, and he didn't tell anything how much that is whether this number is, sorry, I mean to say that the given number, how much large should be. He's not talking about that. That is, the even number should be greater than or equal to 10,000 or 1,000 or maybe 1 lakh, something like this. He didn't tell about this, but he's telling that every sufficiently large. Sufficiently large means what suits you. You can take and then you can write that number in the sum of a prime, and the another term is which is a product of two primes. Fine. So for example, you can take suppose if you are writing q, let us take p equals to 2, and then q, let us take q equals to, this should be product of two primes. So let us take 2 times 3 like this. So 2 plus 2 times 3 like this. So this is going to be 3, and 3 times 2, that is 6 plus 2, 8. Like this there, it's telling. So in the other way also, if you are taking this p equals to 7, and another you can take 7 into 5. Okay, so thing is that if the sum of these two is going to be an even number, it means either they should be these both should be odd or both should be even. So in case of even, there should be 2 also, and this also should be 2, or yeah, this also should be 2. This would be, I mean to say that this should be fixed at least. Okay, because 2 is only even prime number. So 7 and plus 35, this is going to be 42 like this. So the even integer, which is sufficiently large, can be written as in the form p plus q, where p is prime and q is a product of two primes, at most two primes. Okay, at most two primes. And if we are not going to take more than 2, okay. Okay, let us see. Next, so he's also talking about the presentation of even number, which is sufficiently large. And then in 1937, in 1937, there was one researcher, Vinogrado. He proved that every sufficiently large odd integer, he's talking about the odd integer now. So he stated that every sufficiently, in fact, he proved that every sufficiently large integer, large odd integer, okay, large odd integer, large odd integer is sum of three primes. Is sum of three primes. So he's talking about the representation of odd integers, and he's telling that every large, sufficiently large odd integer is the sum of three primes. Okay, so we are, if he can write odd integer as a sum of three primes. Suppose p, q, and r. There are three primes. Okay, so when this odd will become even, do you have any idea what we should do? Of course, we are not going to multiply. We should add something. We should add something, and that number should be odd. Another odd. Okay, another odd. Another odd number. So odd number may or may not be prime. Thing is that odd number may or may not be prime. But he has proved that every sufficiently large odd integer is a sum of 3 primes. Okay. But this odd may or may not be prime. Thing is that, okay, if you want to make it even like this, so every sufficiently large even number, and at least we need this. I mean to say, at least we need this much, these 3 primes. Okay, but this is optional. This may be prime, or this may not be prime. This may be prime, or this may not be prime. Okay, this may be prime or may not be prime. Fine. For example, that 9 is odd, but it is not prime. Okay, 9 is odd, but it is not prime. And 7 is odd, but it is prime. So there are possibility it may or may not be prime. So every odd integer can be written as sum of at most 4 primes. Are you getting what I'm trying to say? If it is prime, then it becomes 4 in total, 1, 2, 3, and 4. And if it is not, then it will be 3 primes. All right. So what we can say, we can conclude that this implies that uh, thus we can say that every sufficiently large large even integer is the sum of at most 4 primes. Is the sum of at most 4 primes. Okay. Now next, in the search of what are how primes are distributed and what they are, or is there any pattern to with the help of which we can find all primes, okay, or is there any formula with the help of which we can generate all primes? Of course, we know that there are infinitely many primes, but there is no sure sort method to calculate that okay, this formula is going to give us all primes. Fine. So in this direction, there is a result, and that results in fact disclaims that a given integer is prime or non-prime. In fact, non-prime. This gives us uh, uh, this gives us a tool with the help of which we can say whether we can claim that a given number is not prime. Thing is that okay. So that let us see that lemma. That lemma this tells that if 2 to the power m plus 1 is prime, then m equals to 2 to the power n for some integer n greater than or equals to 0. All right. So what is there in it? Otherwise, in contrapositive way, we can write it or equivalently. If m is not equals to 2 to the power n, that is m is not of this form, then 2 to the power m plus 1 is not prime. So this gives us a method how to claim that a given number is not going to be a prime. Okay, like this. So let us prove this first, and then after that we will see that some formula kind of thing, which are called in fact Mersenne prime and Fermat primes, or Mersenne numbers and Fermat numbers, with the help of which we can generate some primes. But of course, those formula or those methods, they are not going to give us every prime. In fact, not every numbers which are generated with the help of that formula are going to be prime. So let us see the proof. Proof we will do by contradiction. So let in contrary that m is not a power of 2. That's what we have written here, a contrapositive way. Okay. So this means that so m is going to be of this form 2 to the power n into q. Okay. Because m is not of this of the power of 2, it means this is not going to be even, and this is going to be odd if it is not even. Okay. So where q's must be for some odd q greater than 1, like this. Now let us consider the polynomial. Consider the polynomial that ft equals to t to the power q minus 1. Okay. So this polynomial has a root t equals to minus 1. All right, you know that when you are writing t to the power m minus 1, so t equals to minus 1 is going to be t to the power m is going to be a root of this, or we can say that it is divisible by t to the t plus 1, like this. Fine. So t plus 1 should divide ft. Okay, divide ft, and is a proper factor of ft. ft as q is greater than 1. ओके ये आपका क्या है, ये पावर 1 में है, ठीक ना, और q is greater than 1 है, so this should be a proper factor. It is not like that t plus 1 is going to be the same as t minus 1. All right, this is only factor. So now let us see t, let us put t equals to x to the power 2n, x to the power 2 to the power n, like this. Okay, then gx, this is equals to f, and let us substitute here x to the power n, 2 raised to power n here. So what we will get, let us substitute x to the power 2 to the power n and to the power q minus 1 here. Okay. So what we get, we can write it x to the power 2 to the power n times q minus 1, like this, and x to the power 2 to the power n q times q. This in the power, this number is nothing but m, so we can write like this: x to the power m minus x to the power m, I think -1 or +1, let us see. Okay, here I have done some mistake. I think here should be plus. Okay, sorry, this I forgot by mistake. Okay, so this should be +1. This should be +1 like this. All right. So it means what? We have a gx equals to x f of x to the power 2 raised to power n, and this is equals to x to the power m plus 1. Okay. Now it has if proper factor what was the proper factor? T plus 1, that is x to the power 2 to the power n plus 1 as a proper factor. Okay. Now for contradiction, what we need at least one thing or one example or one case to contradict that the very true things. So taking x equals to 2 in particular, x to the power, sorry, not x, but this becomes what? If you replace the x by 2 to the power 2 to the power n plus 1, this becomes a proper factor of g2, that is x to the power, here we have to substitute x to the power m, sorry, x to the power m plus 1, that is 2 to the power m plus 1. Fine. So can this be a proper factor of this number? No. Which cannot, and therefore our assumption is wrong. Or we can say therefore what we assumed, that x is alpha. Okay, 2 to the power m plus 1 is not prime. 2 to the power m plus 1 is not a prime. Why? Because this becomes now a proper factor of this number. Okay, so if some number having a proper factor, then how come it can be a prime? Fine. Proper factor means other than that number and 1. Okay, so 2 to the power m plus 1 is not a prime. All right. Next result is that okay, let us see Fermat numbers. Okay, Fermat numbers. So in search of primes and its form, it was Fermat who gave a formula to generate prime numbers. Okay, he said that the number of some particular form can generate many primes. Thing is that, okay, or he said that a number of a particular form will generate primes only. Okay, the number, or we can say for n equals to 0, 1, 2, 3, ... the numbers fn 2 to the power n plus 1 is called Fermat numbers. And those which are primes are called Fermat prime. Fermat primes. It means to say, I mean to say that not all are from Fn going to be a prime number. So what Fermat conjectured that Fermat conjecture. That is, he predicted that the number of this form are going to be prime. So he told that Fn is a prime for every n is greater than or equals to 0. So in 1932, actually this was not proved, but in 1932, it was Euler. It is pronunciation of this is Euler. We say Euler. Okay, Euler. In 1932, Euler investigated very deeply this number, and for if n equals to 0, we can get what is called 3. Okay, n equals to 0, so it becomes power becomes 0, and then this is 1, and 2 plus 1 3. Okay, and then f1, this is 5, f2, this is 17, and f4 2 5 7, and no, f2 17, and then I think the f5, yeah, f5 is equals to 6 5 5 3 7. Okay, he found that they are primes. Of course, it is very easy to verify up to f4, but later stages it is difficult to find out. Of course, divisibility rule is there, with the help of which by some effort we can decide. But anyway, this is going to be not going to be easy task. Okay. 0 1 2. I think this is should be 3. Yeah, this should be 3. This should be 4. Yeah, I missed it. So this is 3, and this is 4. All are primes. But next, for n equals to 5, so f5 is equals to 2 to the power 5 plus 1, and this after computation is this after computation can be written as a product like this 4 2 9 4 9 6 7 2 9 7, like this. Of course, one may guess that after F2 we are getting 7 in the end. All right, but we cannot say as of now that it is going to be 7 or something. And merely being 7 in the end, it is not going to say whether it is prime also, because you know 27, 7 is there in the end, but it is divisible by 3 and 9 also. And this can be written as a product of 6, 4, 1 times 6, 7, 0, 0, 4, 1, 7, like this. So this F5 turns out to be composite. So F5 is composite number. It is a composite number. So what is the conclusion? So based on this, Euler concluded that there may be many Fermat primes, but they have not been founded of course. So he told that every Fermat number is not prime. Okay. So of course there may be many. There may be many Fermat primes, and the numbers. This F0, F1, F0, F1, F2, F3, and F4, because they turn out to be turned out to be primes. So therefore they called Fermat primes. Okay, F5 is not Fermat primes, and in general Fn is called Fermat numbers. So there may be many Fermat primes, but they have not been found yet. They have not been found yet. And there is a result that there are infinitely many Fermat primes. That one can see or look for the proof. There are infinitely many Fermat primes. Okay, so you can do it. All right. Another result is that the distinct Fermat prime numbers are relatively primes. So this is another result. Although all Fermat numbers are not prime, but there is a result which says that distinct Fermat numbers Fn are mutually coprimes. Okay. So this is what we can have. ये तो प्रूफ नहीं हो पाया कि सारे Fn जो है वो प्राइम है, because we have F5 and so many numbers also in the form of Fn which are non-prime. But thing is that interesting part that distinct Fermat numbers Fn are mutually coprime. So let us see the proof. Let Fn and Fm are distinct Fermat numbers. So Fn we can write 2 raised to power 2 to the power n plus 1. Fm 2 to the power 2 to the power m plus 1. Let the greatest common divisor of Fn Fm equals to d. Now we claim that d is equals to 1. And once it comes out to be 1, then we can say that they are relatively prime. Fm and Fm are relatively prime. Okay, so here 2 to the power n plus 1 is congruent to, of course, a congruence relation we'll be talking about later, but this much information at least you must be knowing. I guess I gave a lecture on it while discussing linear algebra. Oh, sorry, group theory. Anyway, this much you must be knowing. So this is congruent to 0 modulo d, because d is the greatest common divisor of n fm and fn. So it must divide fm and fn both. All right, it must divide. So it should be multiple of d. This number fn should be multiple of d, and also fm also should be multiple of d. So we can write like this: plus 1 is congruent to 0 modulo d, 0 modulo d. And then using the property of congruence modulo n, 2 to the power 2 raised to power 2 to the power n plus 1. Let us subtract them side by side. Plus 1 is congruent to 0 modulo d. And then the left hand side, let us cancel them. So we have 2 to the power n minus 2 to the power m is equals to 0 modulo d. Okay, it means what? It means that this is going to be multiple of d, or d divides this one, d divides this number, and because n and m, because they are even numbers, okay, because they are even numbers, so it means what? D must divide 2. Okay, they are even number, so D must divide 2. And if D divides 2, it means that either D equals to 1 or D equals to 2. Either D equals to 1 or D equals to 2. But we say that D cannot be 2. Why? Hello. Hello.
Yes, sir.
Yeah, why D is not 2? Why D is not 2? So you can find it out why D is not 2.
सर दो प्राइम नंबर्स है ना एफएन और एफएम, उनका जीसीडी 2
Yes.
हो ही नहीं सकता। सर दो प्राइम नंबर है एफएन और एफएम, उनका जीसीडी 2 नहीं हो सकता।
They are not prime. Just we have seen they are not necessarily prime.
सर एफएन और एफएम दो ऑड नंबर है तो उनका जीसीडी 2 नहीं हो सकता इसलिए।
Yes, that's okay. Because they have this form, na? 2 to the power 2 to the power m.
Yes.
Yeah. So as okay. So you know now you know the reason. Okay. So this means that d has to be equals to 1. It means what? They are relatively prime. Okay. So this proves the result. Okay. We have time or what? We have 5 minutes more. There is another form of number which is called Mersenne prime. Mersenne prime. Mersenne numbers, and of course this is similar to the Fermat numbers, Mersenne numbers. Okay, and all Mersenne numbers are not prime. Okay, so integer. Uh, the numbers of the form, sometimes it is written as mn equals to 2 to the power n minus 1. Okay, where n is prime, is called uh, the numbers are called, okay, are called uh, Mersenne numbers. Mersenne numbers. They are called Mersenne numbers, and Mersenne studies in 1644 around about this, and the number which are prime among them are called Mersenne prime. Uh, the numbers which are prime among these, okay, among these are called Mersenne prime. Are called Mersenne primes. So, like we have seen in case of Fermat numbers, okay, here also we can have because n can be only prime. That is, in general, we can write if p is, let us denote n by p because they are prime. So we can write 2 to the power p minus 1 and take p equals to 2 because p need to be prime. So m2 is 2 to the power 2 minus 1. So this is a 3, and similarly m3 is equals to 7, m4 not 4, m5. Okay, m5 equals to 31, and m7 this equals to 127, and so on. So they are all primes. They are primes, but m11 this is equals to 2047, and this can be written as product of 23 and 89. So they are a product of two which is not prime. Which is not all right. So in fact, in the book, I don't know in which year the book I'm referring was written. maybe 10 or 15 years back or so, yeah, or maybe early. So by that time, around 35 Mersenne primes were found. Okay. A few years back, as per the information in book, only 35 Mersenne primes were found. So unlike we have a result for Fermat numbers, Fermat primes, there are many, there are infinite many Fermat primes like this. So there, what we say, there is no result for Mersenne primes, that there are infinitely many primes. Okay. So it is not known whether they are finite or infinite. All right. As in case of Fermat primes, it is not known. It is not known. It is not known whether there are finitely or infinitely many Mersenne primes. Whether or whether there are finitely or infinitely Mersenne primes. And also one more thing. One thing I think as in case of, okay, just a minute. Here I think I have written there are infinitely many Mersenne primes or Mersenne numbers. I don't know what I have written. I need to see. Sorry, in Fermat case, Fermat numbers. There are no. There are every Fermat number is not Fermat prime. Is not prime. Okay, there are many Fermat prime. There are infinitely many. Okay. In fact, I was trying to say that not primes. They are not. I think it is not proved. Infinitely many Fermat numbers. Okay, so of course it depends on n. Okay, I think I forgot these things. Okay, so it was not. It is not proved there are infinitely many Fermat primes or what. So similar is the case with the Mersenne prime also. Okay, but and one result is that the distinct or the different Mersenne numbers are mutually coprime. So this result is similar to that of Fermat numbers. Okay, fine. So this was what for today. I'll update whether there is any proof for that there are infinitely many Fermat primes or not until now, because I referred only book. We need to see some more research paper if there is any update on it. Okay, so I'll let you know tomorrow if there is anything. Fine. So let us conclude the discussion for today.
Thank you for watching this video. To stay updated, Please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.